In this lecture, we are going to talk about intermolecular forces. So these are the forces that exist between different molecules. So we're not talking about bonding anymore. We're talking about the interactions among two completely separate molecules. So the state of matter depends on the magnitude of the intermolecular forces relative to kinetic energy. And so we have to think about what kinetic energy means as well as the intermolecular forces. So for a solid, the intermolecular forces are really strong and the kinetic energy is really low. So we end up having greater intermolecular forces, slower kinetic energy, and that is what causes a substance to be a solid. For liquids, there are moderate intermolecular forces and there is movement, so there's some kinetic energy. And then for gases, these have the weakest intermolecular forces, and that's because the molecules are the most spread out. So much like with bonding and Coulomb's law, we have to have two molecules have to be within close enough proximity in order for the molecular forces to be significant. So these intermolecular forces are less strong for gases as they are more spread out. So we are looking again at these electrostatic forces. So that kind of means charges. So it's based on interactions of opposite charges. And these exist between atoms and molecules. So you can kind of think of it as that's holding the particles of this substance together. And so for a solid, you have low and increasing intermolecular forces, low kinetic energy. And for liquids, you have moderate intermolecular forces. They are not as strong as the solid, and the increasing kinetic energy, and that goes up with temperature. And then gases have the most kinetic energy. They have the least strong intermolecular forces because, again, it has to do with how close they are. So intermolecular forces rely on molecules being close enough to have that charge-charge interaction happening. So let's think about some ways that we can actually change the kinetic energy of molecules. So we could change the temperature. We could adjust the pressure if we're talking about gases. And we could also energy with electromagnetic radiation. So remember when we worked with electrons jumping to higher energy levels, if you zap them with some sort of light energy. And so at low temperatures, we tend to have solids, and at high pressures, we would have solids. And then as it heats up, we get a liquid and then gases. And then as we increase the pressure, we go this direction. So low pressure, high temperature, high pressure, low temperature. So we can kind of think of this example here. You've got these molecules moving around in this container with a movable piston. And as you compress this piston, the area in which the molecules occupy, it decreases. And so you could kind of imagine that you've got these compounds, and as they're getting compressed together, you could start to form liquid. So they're being forced together in a smaller and smaller area. So increasing the pressure kind of has, it's similar to decreasing the temperature. And then you could also think of zapping these things with energy, with like light, right? So for ultraviolet light, there's enough energy to actually break bonds. And with IR light, things just move. And then microwaves, they also rotate. Okay, so they vibrate or rotate. So you can think about how if you're hitting them with a lot of energy, you're going to disrupt the covalent bonds. That will change how the molecules interact with each other. And if they're vibrating or twisting around, that will affect how long those intermolecular interactions can actually take place. So let's take a look at water. Water is a really unique substance. It has a special kind of intermolecular force, which we will introduce in a little bit. But for now, I want us to think about what is happening when you have liquid water and you are boiling it. Okay, so imagine you have this pot of water on the stove. And as it's heating up, the molecules are moving more and more and more. So which image is showing water vapor? It's A. So think about this. What we're saying is we aren't breaking the covalent bonds between hydrogen and oxygen atoms. So this is wrong here. We are not separating the water into its components of H2 gas and O2 gas. All that's happening is we now have water vapor. It's still H2O, but now it is H2O gas instead of H2O liquid. So phase changes only disrupt the intermolecular forces. They do not change the covalent bonds of a molecule. So let's think about where these intermolecular attractions come from. What causes these IMFs? Well, it's just like we said with the covalent bonds, Coulomb's law. So electrostatic attractions, ionic bonds come from a full positive and a full negative in being attracted to each other, like we see here. Covalent bonds are when the electrons are attracted to the nuclei and there is a sharing of electrons. And then we can also see that there are partial charges can cause these molecular attractions. So we have a partial positive on this hydrogen here and a partial negative on this oxygen here, and those are attracted to each other in a similar fashion as our ions are. Now, the magnitude of the attraction is less, right? Because Coulomb's law dictates that as the charge's magnitude increases, the attraction increases. So the magnitude of this is smaller. So the overall attraction is smaller, but there's still an attraction between two charges. It's just two partial charges instead of two complete charges. So this happens when we have polar molecules. This happens when we have ions. And IMFs are driven by these partial charge attractions. So over here we have our intramolecular attraction, so molecules either between two separate ions forming a crystal structure as we have here, or the covalent bond that forms between two atoms. And then over here we have these partial charge attractions, and that is what causes the intermolecular forces, or IMFs. So let's just talk about the polarity of molecules briefly. If we have the dipoles canceling, even if the bond itself is polar, you can see from this electrostatic potential map here that there's no distinct pole of positive and negative. There's two negative regions and a positive region. So this does not have a distinct pole. This is a nonpolar molecule. Water, on the other hand, the two dipoles add up this direction. And so we have this pole. We have a negative, partial negative region. And down here we have a partial positive region. So this molecule, you can see, has a pole. It has two poles. So this is a polar molecule. If you would like to play around with polar molecules and practice identifying them, check out these two simulations where you'll actually be able to change the electronegativity of two atoms and look at how the overall polarity of the molecule changes. So what this really is showing you with this electrostatic potential map is the distribution of electron density. And so here we have equal distribution on both sides, and here we have more electron density in one region versus another. So intramolecular forces, those are within a molecule. They keep the molecule together. Those are the chemical bonds. The intermolecular forces are the attractions between molecules, and these are weaker than the intramolecular forces. So looking at HCl, again, this is a polar molecule, so we have a partial positive charge on the hydrogen and a partial negative charge on the chlorine. This covalent bond has a value of 430 kilojoules. So in other words, remember, it costs energy to break covalent bonds. So that means that you have to put 430 kilojoules of energy into this bond to break it apart. Whereas the intermolecular force, that is a weak force, and that only requires 17 kilojoules to disrupt that attraction there. So we're going to talk about now the different types of intermolecular forces, where we'll cover dispersion forces, dipole-dipole forces, hydrogen bonding, and ion dipole forces. These are peer presented from weakest to strongest. So our dispersion forces are the weakest of these, and our ion dipole are the strongest. So dispersion forces are from temporary dipoles, and they are due to the fact that electrons are not in one spot. They move around all the times, because remember, we can't know the location of an electron. The Heisenberg uncertainty principle tells us that we can only know its energy and not its location. And so we have those orbitals as a way to say, well, the electron must be somewhere within this space. So here we have an example of an orbital. Kind of looks like an s orbital. It's our sphere. And we see that we have 2 electrons in this orbital. So this looks like an atom of helium. And you can see that you have both electrons are in different spots. So imagine that we're taking snapshots, and instead of knowing the energy of these, we know their location. So in this instance, they are in this location. And then here, they're in different locations. And then over here in this instant, they're both on one side. And so that introduces a temporary dipole. So now we have a partial negative and a partial positive, but it won't stay there because in the next frame, they'll move again. And so it could be that both electrons now come over here. So instead of the dipole looking like this, it could be switched. So when this happens, we start to see attractions forming between 2 atoms. So in this case, we have this positive end and it's attracted to this negative end. And so we have a dipole-dipole interaction, but these are temporary, so they are very weak. So here is kind of a video showing you what this looks like. So as they form, you get that dipole-dipole bond, but the electrons have to move around in the right spot and end up in the right spot. Okay, so they are constantly moving, so the dipoles are constantly forming and disappearing. These induced dipoles cause attraction. As they get closer to each other, they get more attracted to each other, and we start to see this interaction forming. So you may have also heard of these as called van der Waals forces. So for our purposes, we will say that London dispersion forces and van der Waals forces are the same. And while they are the weakest of the interactions, it's not always the case that they don't have a great effect. So, interestingly enough, these intermolecular forces, these weak dispersion forces, are what help geckos climb walls.
We wanted to know how things could climb. And so we picked the gecko. They're spectacularly good at that. We didn't know why. They can run up a wall at 1 meter a second and take 30 steps in that 1 second and pull their toes off in milliseconds, thousandths of a second. And we didn't know how they could do that. So we zoomed in on the toes, and what we found is the toes have these leaf-like structures with millions of hairs. They kind of look like a rug. And each individual hair has the worst case of split ends possible, to 100 to 1,000 split ends. And it's those tiny little tips, those little split ends, that get very close to the surface. And they stick not by glue or by suction or like Velcro, but they actually stick by intermolecular forces alone. We never thought about making an adhesive out of hairs, until we looked at the gecko. And we believe that engineers would never have looked at this kind of solution for a novel adhesive. It just shows how important curiosity-based research really is.
So what's next? How about an entire robotic gecko? That's pretty much the idea behind StickyBot, developed at Stanford University by Professor Mark Kokoski and designed by his doctoral student Songbek Kim. It was inspired by Bob Full's gecko research, and it's the first robot that can actually scale smooth vertical surfaces.
Learning from nature really actually is a two-way street. So biologists like us discover the general principles of function, give those ideas to the engineers. They build something that's never been built before. In doing that, they have lots of questions, and they then generate ideas to allow us to go back and discover new things about the animals. So there's a real synergy when it works well.
So I hope you found that little tidbit of research interesting. Bob Full works at Stanford, and he actually works in a lab that takes a lot of designs from nature and tries to mimic them. So he's a biologist, and he works with engineers to build things that come out of nature. And so what they found was it's because the geckos have all of those split end hairs on the ends of their toes. What's happening is that allows a gecko to have very good contact between a surface and their hairs. And so it is those those induced dipole, those dispersion forces or van der Waals forces that's those attractions that allow a gecko to climb a wall. And in another group that studies geckos, they found that a gecko could hold up to 90 pounds just from those weak intermolecular forces, but it is the sheer magnitude of the number of molecular forces that they have. So while they are weak by themselves, they are actually quite strong all together. So let's think about why boiling point increases with size. So these are our normal gases here. And we see that as the molar mass increases, our boiling point increases. So as the atom gets bigger, the electrons are held more loosely by the nucleus, so there's more freedom for them to move around, and so they can more easily form those temporary dipoles, and that relates to the higher dispersion forces. Halogens exist in different states. Fluorine and chlorine are gases, bromine is a liquid at room temperature, and iodine is a solid. It's for that same reason. Okay, so we have, as these get bigger, we see less, the electrons are held more loosely, and they're able to form those dipoles. Now let's look at a more complex molecule. So here we have N-pentane. So that means this N stands for normal, and it's pentane because there's 5 carbons and there's no double bonds anywhere. So it's an ane. So it's an alkane molecule. And we see that it has a molar mass of 72.15 grams per mole and a boiling point of 36 degrees. If we look at neopentane, so it's still got 5 carbons, but it is in this weird shape here. Molar mass is the same, but our boiling point is now 9 degrees Celsius. So why does N-pentane have a higher boiling point than neopentane? Well, it has to do with the fact that there's more area for interaction compared to this one. So this is like comparing our fingertips to a gecko's toe. Our fingertip has much less space or much less contact area between our fingertip and the table if you were to put your hand on the table. The gecko has much more contact, so it has a large area for interaction, and so that's why the gecko can climb a wall and you can't. It's the same concept for why N-pentane has a higher boiling point than neopentane. And so this is kind of the trend. So as you get a small contact area, you get the weakest attraction. And as the surface area gets larger and you have greater attraction, you have greater intermolecular forces. There's more of them basically was what's happening. There's intermolecular contacts between this whole area versus here. So the area of this rectangle, if you were to count the area, is the smallest here and it's the biggest here. So that is why this molecule has a higher boiling point. So you can kind of count these points of contact, and it gives you an idea as to why you'll end up having a higher boiling point here. So for straight chain molecules, our boiling point increases with molecular weight. So let's try to predict the boiling point of 2-heptanone. So this guy has 7 carbons, and it's heptanone because this is actually a ketone here. That's what a double bonded oxygen sticking off of a carbon that's bound to other carbons. So this is heptanone, and you do not need to know how to name these compounds. I'm just telling you where the names come from. If you end up taking organic chemistry, you will get lots of practice naming these. So if you're going on to organic, don't worry about learning this now. You will not be tested on it in this class. So can we predict the boiling point of 2-heptanone? So its molar mass is 114.8. And so if we look at where it is in here, so here's heptane, here's octane. So we probably would expect it to be somewhere in here, right? Turns out that it isn't there. It's actually got a higher boiling point than even nonane, which has 9 carbons. So the boiling point of 2-heptanone is much larger than the boiling point of heptane. So why is this? Well, if we look at this, we have that double bonded oxygen versus where you have something like octane, which has basically the same molar mass, but still lower boiling point. This just has carbons and hydrogens. So the only intermolecular forces that are available to octane are those dispersion forces that we've talked about, because the electrons are shared equally between these carbon and hydrogen bonds. This is a non-polar molecule. But for heptanone, because oxygen has a partial negative on it, and this carbon has a partial positive, now we have this unequal sharing of electrons. So this region of the molecule is polar. This is all still non-polar over here, but this region has a distinct pole. So these dipole forces come from permanent dipoles due to partial charges. So we distinguish dipole forces from the induced dipole forces by calling these other ones, the weaker ones, dispersion or van der Waals forces. So when we say dipole, we are talking about molecules that have permanent dipoles due to differences in electronegativity. And since oxygen is so much more electronegative than carbon, the electrons spend most of their time down here by this oxygen, and we see that we have a distinct pole with a partial negative charge here and partial positives here. So these interact much the same way that we saw those water molecules interacting, where we have this partial negative here and this partial positive here. So let's look at our octane and heptanone. Here we have only dispersion forces. And here we have dispersion forces and a dipole force. So these molecules are interacting with each other with stronger intermolecular forces than these are, which means that it requires more energy to disrupt these interactions for heptanone than it does for octane. So let's look at ethanol and ether. So these compounds have the same molar mass. They are isomers of each other because we have the same molar mass, but they're connected in different ways. And the boiling point of ethanol is 78.3 degrees Celsius, and the boiling point of ether is negative 22. So ether is, while you have a liquid at room temperature in a closed container, if you open a container of ether, it's just going to evaporate. So this is why it's really useful. It used to be really useful as an anesthetic, because they'd put it on a rag and then you'd breathe it in because it's vaporizing on that rag. So that's why it was used as an anesthetic for surgeries in the olden times. And if you ever saw cider house rules, you've kind of seen what that looks like. So our molar masses are the same and our boiling points are really different. And so the key here is this OH for this, for ethanol, and there's not really a section like that for ether. So what that is it's special type of dipole-dipole bond called a hydrogen bond. And this is due to polar molecules that contain hydrogens bound to a nitrogen, an oxygen, or a fluorine. It is only ever these three, okay? Because that is where we have an electronegativity difference that it is significant enough. A hydrogen bound to a carbon cannot participate in a hydrogen bond because the electronegativity difference between carbon and hydrogen is much too small. But the electronegativity difference between nitrogen, oxygen, fluorines, and hydrogens is much greater. So what happens is you get this polar covalent bond, just like we've talked about with water, and then you have this interaction, and this is a hydrogen bond. And this is pretty much how they're always shown, where you have the covalent bond as a straight line, and then you have a dashed line to show hydrogen and oxygen interacting with each other. So here we see for ethanol, we have this delta negative, the partial negative on the oxygen, interacting with that partial positive on that hydrogen. And while hydrogen bonds are a type of dipole-dipole interaction, they are very strong, because the electronegativity difference here is much stronger, is much greater than for other types of dipoles. So let's take a look at this little simulation. So here we have a bunch of water molecules, and it's not moving right now, and you can see these little dashed gray lines have our these are our hydrogen bonds, okay? And then we have our partial positive hydrogens and our partial negative oxygens, and that's where that hydrogen bond is interacting. And so then as these molecules move around, you'll see that the bonds are constantly breaking and forming. So there's kind of an equilibrium going on where you have the molecules, they do move around because this is liquid water. And so you can see how they're constantly forming and breaking and forming and breaking. Okay. So feel free to come to this simulation and play around with it if you'd like to get more practice with it. So water has a really high boiling point than most other similar molecules, and it's due to these hydrogen bonds. Because we have that very strong interaction. Now, H2S, this is from the same group. The electronegativity difference between sulfur and hydrogen is not enough to make that hydrogen bond. So in order for a hydrogen bond to happen, you have to have an electronegative atom that has a lone pair of electrons. That's the oxygen. And then you have to have a hydrogen attached to an O, N, or F. So that's the hydrogen of the hydrogen bond. So we often call this the hydrogen bond donor and this the hydrogen bond acceptor. So these molecules are nonpolar because there is not enough of an electronegativity difference to see this change. Water here is polar, so it has a very high boiling point. And in fact, without hydrogen bonding, the water on Earth would be gaseous. So water is a really, really weird liquid because of its ability to hydrogen bond. So you may have seen people adding salt to icy roads. It's not something that we do much often here in the Pacific Northwest, but when I lived in Indiana, we did this all the time. And so by February, the roads were so covered in salt that it was really, we didn't get a lot of ice formation. And so what's happening is in liquid water, these hydrogen bonds are constantly breaking and reforming. And we saw that in that demo we just watched. Ice has stable hydrogen bonds that hold these molecules apart. So you can see the space between these molecules is smaller than the space between our water molecules that are in a solid, so ice. So what happens is, this is why ice floats. This is why ice is less dense than water. So this is another weird thing. Most liquids, their solid is denser than their, their solid is denser than the liquid, but for water, that is not true. So life on Earth would look very, very different if water didn't have this ability to form hydrogen bonds. Okay, so when we have salt interrupting this structure, what happens is the hydrogen bonds break because the positively charged hydrogen atoms are attracted to the negatively charged chloride ions, and the partial negative oxygens are more attracted to the partial positive sodium. You might be thinking like, well, but doesn't it cost energy to break the hydrogen bonds? Yes, it does. However, the energy you get back from reforming these bonds is greater than the energy you get back from reforming these. So this is why sodium chloride, is able to disrupt the hydrogen bonding in ice. And so that lowers the point at which the network forms. So because it lowers the energy, and it lowers the place at which water can go from liquid to solid. So these are called ion dipole forces, and they result when polar molecules are attracted to ions. So these are permanent dipoles that we're talking about. So when we say dipole, we mean permanent dipole, not the induced dipole van der Waals dispersion forces. So when you have an ion like chloride, you've got these partial positives of hydrogens interacting with it, surrounding it. So this is how salt dissolves in water. The water bunches around the chloride ions, and then the water also bunches around the sodium ions, but that's the oxygen, the partial negative oxygen is what's attracted to the sodium there. Okay, so this is how a salt dissolves in water, and this happens because this dipole of the the molecule with the permanent dipole is attracted to the ion, the full charged ion. So to summarize, here are the types of intermolecular forces, and we talked about dispersion forces. So remember that these can become very strong if you have high molar mass or a ton of them, right? So like the gecko foot, tons and tons of interaction points between the hairs of a gecko and a wall. And so that's why a gecko can climb a wall, whereas you cannot. Dipole, those are between polar molecules, and they're about here, this energy. For hydrogen bonding, so again, remember, you have a lone pair on a F, O, or N, and then you have a hydrogen attached to an F, O, or N, and that's where we get those hydrogen bonds. So for practice, go check out ammonia. Draw the Lewis structure for ammonia, NH3, and determine if you think that one can hydrogen bond or not. And then finally, we have the ion dipole, where this is where you get mixtures of ionic and polar compounds. So you get a charge, and it gets surrounded by these polar compounds here. Okay, so again, what you'll want to be able to do is recognize which intermolecular forces are present when you're shown an example of interaction, and you'll want to be able to predict behavior of a molecule based on that. So can you predict boiling point? Can you predict how molecules will interact with water?